Hello everyone, and thank you for watching my talk on revisiting the effect of phase transitions on layering of mantle convection. This is work I did together with René Gassmüller, Carolina Lufko-Bertoloni, and Lars Dixrood. And why are we interested in phase transitions? So we know that they are important for mantle convection for a long time. This is a study from 1992 with different convection models. The model on the left shows a mantle convection model without phase transitions, and the convection model on the right is with phase transitions. The black contours show the temperature, and they show that on the left, upwellings and downwellings can go through the whole mantle, whereas on the right, they are impeded at the 660 phase transitions and cause a more layered style of convection. Now, we know today that this is not the case in the Earth, so we know that plumes and slabs can actually cross from the upper to the lower mantle and the other way around. But this nevertheless shows how important phase transitions are, and these models also show a different effect. So what we see here on the right is the time averaged mass flux on the horizontal axis plotted over the depth of the model. The solid line is a model without phase transitions, and the dashed lines are models with phase transitions. So the 660 has a Clapeyron slope of minus 2.8 megapascal per Kelvin. We see that the flux is impeded, so there's less material that can pass through. But we also see that the different phase transition width causes more or less material to flow through. So the wider the transition, the more material can actually pass from the upper to the lower mantle. We also saw that this effect is really strong in our own models. So what we see here are convection models in a 2D box with a setup of Christensen and Yuen in 1985. They have a Rayleigh number of 10 to the 5. They are heated from the bottom and cooled from the top. We see the temperature as background colors, and then the black lines are the streamlines of the flow. These are 3 different models. They all have a phase transition in the center of the box, and what's different between the models is just the width of the phase transition. So on the left, it's 5% of the box height, and in this case, we have whole matter convection. In the model in the center, it's a little bit thinner, so it's 4% of the box height. And here we have episodic convection. So some material remains in the upper mantle, some remains in the lower mantle, and some can go through. In the model on the right, where the phase transition is even thinner, only 1% of the box height, we now have layered convection. So most of the material in the upper mantle remains there, and most of the material in the lower part of the model remains there. And we also see that the temperature is very different between these different models. So modeling the phase transition width accurately is really important. Now, if we look at phase transitions in the real Earth, we see that they are more complex than just having 1 or 2 transitions. These are the phase transitions for a pyrolytic composition. We see that there are lots of different transitions with different phase transition width, different Clapeyron slopes, and some of them exist only in certain pressure or temperature ranges. We also see that the material properties jump at these phase transitions. So what's shown here is the thermal expansivity, which changes a lot between the different phases. And this is also true for the density and for the specific heat. And what we can see is that if we have one specific adiabat, so for present day, for example, this yellow one shown here, we go through a specific set of phase transitions. But then if we are on a colder adiabat for a slab or a hotter adiabat for a plume, or if our average adiabat would just be different, for example, in the early Earth, we might have completely different phase transitions. So some phases just vanish for higher temperatures, like what's there at ringwoodite. So what can we do to actually include all of these effects in a geodynamic model? There have been a number of different methods for modeling phase transitions. One method is the phase function approach, which has been used for a long time. And this one describes the phase transition as a function like a hyperbolic tangent, which describes the proportion of each stable phase independence of depth. The advantage of this is that it's easy to implement, and it's also easy to change variables like the Clapeyron slope. The disadvantage is that each phase transition has to be implemented by hand, which limits the complexity of the phase relations. A more recent approach is the use of lookup tables that contain material properties for a range of temperatures and pressures. And these lookup tables are usually computed with mineral physics toolkits and are based on a mineral physics database. Now, this allows to include multiple phase transitions with different thicknesses and Clapeyron slopes and temperature pressure ranges, so those can all change. However, both of these methods have a disadvantage, which is that if we want to model the latent heat effects accurately, we have to resolve the width of the phase transition with several mesh cells in the geodynamic model. And otherwise, we don't accurately capture the temperature change. And we can imagine if global 3D convection models usually have a resolution of several tens of kilometers, that limits how we can include thin phase transitions. We can think about the problem like this. So if we have a thin phase transition in the real world, like shown here on the left, where we see it in pressure and temperature space, we have a phase 1 and a phase 2, and then a really abrupt change between the two. If we look at the temperature change, we have to look at the mantle adiabat. So if we are in phase 1, we increase in temperature as we increase in pressure. At some point, we hit the phase transition. Then the adiabat changes its slope abruptly and goes along the phase transition until everything is converted from phase 1 to phase 2. And then the adiabat continues to increase in temperature as it increases in pressure. So that means the slope of the adiabat is different, but only if we're exactly on the phase transition. If we're a little bit above or a little bit below, then we don't predict this change of slope and temperature. So what does that mean when we go from the real world to our numerical discrete model? First, it means our phase transition has to have a given width, which is just limited by the resolution of our model. And there are two different resolutions. One is the resolution of the geodynamic model. The other one is the resolution of the lookup table. And both have to resolve the phase transition. But if the phase transition is discontinuous, then this is not actually possible. And if we're just slightly above or slightly below, we will completely mispredict the slope of the adiabat as it goes through this phase transition, and then we come out at a different temperature after we have crossed the phase transition. And we can look at a geodynamic model to see how this actually looks like. So these are two different models, again, with a phase transition in the center of the box and otherwise a 2D convection setup. And on the left, the phase transition is resolved. So this is a wider phase transition. And we see that there's upwelling on the left. So as it goes through the phase transition, it changes in temperature and it increases its temperature. On the right, we have a model where the phase transition is much thinner, so it's not resolved by the model. This abrupt jump in temperature, this shows the initial condition of the model, which has the similar temperature jump as in the model on the left. But then as the model starts to move, we see that all new material that crosses the phase transition, it does not actually include this jump in temperature. Either it doesn't change its temperature at all, or it has a wrong jump in temperature. And so these artifacts are what happen if the phase transition is not properly resolved. So how can we solve that problem? One idea is to solve the equations in entropy space instead of temperature space. If we look at the whole problem in entropy space, what we see is, so we again have phase 1 and phase 2, and we have an adiabat, but now the adiabat doesn't have a kink. It's actually a constant. It's at constant entropy because the adiabat says no energy should be exchanged with its surroundings. The other thing that's important is that now the phase transition is no longer discontinuous, but it has a finite width. And that's exactly that part where the adiabat is on the phase transition. And that means if we are slightly to the right or slightly to the left, like not exactly on our adiabat, we still predict a reasonable slope or a reasonable release of heat along that path. And this is not so sensitive to the resolution anymore. We can also look at how that would be implemented in a geodynamic model. So we are using the geodynamic modeling software Aspect and the mineral physics toolkit Festo. And what we do is we solve the energy equation for entropy instead of for temperature. That means that the adiabatic heating term, for example, which contains the thermal expansivity, which has all of these jumps, this is now automatically included in the entropy S. And the specific heat, which also has lots of jumps, is now only included in the diffusion term. Otherwise, we can see that the structure of these equations are really similar to each other, so we don't actually need any new numerical methods to solve them. But our new equation now contains both the entropy S and the temperature T, and so that means we need a lookup table where we can convert between the temperature and the entropy for each point in the model. And that's what we compute using Hephaestus. The other part of our method to accurately model phase transitions is in the mechanical part, so in the Stokes equations, where we have the mass and momentum conservation. And what we do there is in the mass conservation equation, we include the time derivative of the density, which is usually not included because it causes pressure oscillations. And we found a method for how to include this term, and this allows it to accurately model the volume change of material as it crosses the phase transitions. Now, let's look at our example case where the thin phase transition was not properly resolved. That's again what we see here on the left. And on the right, we now see the new method, and the phase transition is actually infinitely thin. But even though it is so thin, the temperature jump can still be resolved correctly as material moves across the phase transition. We can also look at the benchmark scenario for this new method. So what we see here is 1D adiabat, where we test if we get the correct adiabatic temperature in the end. So left is shown the model setup in temperature and pressure, and on the right we see the density, the temperature, and the entropy and how they evolve over time. And specifically for the density, the black profile shows the reference profile, so the profile the model should have at the end. And the brown profile shows the initial condition. So this is one adiabat, and then material comes in with a different temperature that's on a different adiabat. And we see how the properties change over time. So let's start the animation. We see the material starts to have this new density. It also has a higher temperature, and it has a different entropy. And the entropy basically stays constant. As this higher temperature reaches the phase transition, it now accurately models the new temperature jump. So we see here material at the phase transition. It crosses the transition, and now we have a new temperature jump at a different temperature. We see that the entropy stays constant at the new temperature, and the brown density profile has now approached this black reference profile. We can also look at how this method performs at an application model. So in this model, we see it's a 2D convection model that has a very thin and strong phase transition that's in this depth region. At the top, we see the temperature, and as these contour lines, we see the density. At the bottom, we see the entropy in the model. And what we see is that both upwellings and downwellings, because of the thin phase transition, they get impeded and they stall as they reach this phase transition, and then only later in time the material moves upwards or downwards through the whole mantle. So to summarize, we have developed a new method that can accurately model thin phase transitions with a reasonable computational effort, so we don't have to resolve the phase transitions of several mesh cells anymore. And the new method includes first solving the energy equation for entropy instead of temperature, and then including the full gradient and time derivative of the density in the mass conservation equation. And this allows it to incorporate a complex set of phase transitions with a variable Clapeyron slope, material property changes, and a variable pressure and temperature range. And we hope that will be useful for modeling all kinds of different convection scenarios with phase transitions in the future. Thank you.